Hi, this is Chintan Patel. In this lecture, we are going to look at the new chapter, that is nothing but the strain energy. So, we are going to look at the few basic concepts related to the strain energy, resilience, proof resilience, modulus of resilience, and one short derivation. So, each and everything is going to be helpful for the application of the strain energy based example, and it is also very important for the competitive exams like the GATE and everything. So this topic is very important. So we are going to start with the basic definitions of this chapter, and let's get started with the first definition, that is nothing but the strain energy itself. So how do we define a strain energy? For the perfect definition, we have taken one example over here. So if you just read it out so that you can easily understand. Let's say some load is attached at the hanging wire, okay, and it extends due to the load. The load moves downward by an amount equal to the extension of the wire. Due to the extension, this happens. A little consideration will show that the load moves downward, it loses its potential energy. So whatever the potential energy is lost by the wire, that energy is absorbed in the stretched wire. So energy can neither be created nor be destroyed, and that is why here only the conversion is happening. What conversion that we are talking about? It is the conversion that the load is going downward, and as it is going downward, it will lose its potential energy that will be absorbed by the connected wire. So this energy may be released by removing the load. So whenever you remove the load, this energy can be released. On removing the load, the wire will spring back to its original position, and this energy which is absorbed in the body when strained within the elastic limit is known as a strain energy. So this is the complete definition of strain energy. So simply we can say that whenever a body is strained up to an elastic limit, when you remove that particular load, as the load was within the elastic limit, the material will try to regain its original condition. It is only possible if the material had absorbed that condition, absorbed some part of the energy that is required for the deformation, and that energy releases back whenever the load is removed from the body. So basically the energy which is absorbed during the straining of the material, or whenever the material is strained, that part of the energy which is absorbed in the body is known as a strain energy. It has been experimentally found that the strain energy is always capable of doing a work. So the amount of strain energy in the body is found out by the principle of work. So basically what we are going to do, we are going to find out the work formula mathematically. Strain energy equals to work done. So this is the basic formula. Now how other parameters are defined, that will be explained. First parameter based on the strain energy is resilience. So what is resilience? It is a common term used for the total strain energy stored in the body. Sometimes the resilience is also defined as the capacity of the strained body for doing the work. So simply we can say that whenever a body absorbs the energy, the total amount of strain energy that has been absorbed or stored in the body is known as the resilience. It is also the capacity of the body to do the work. So resilience is total amount of strain energy absorbed. What is proof resilience? It is used for the maximum strain energy. Now we know that the strain energy may change at some time. It might be maximum at certain time frame, and it might be the minimum at a certain time point. So the maximum strain energy which can be stored in the body. It is the maximum limit of the body. This happens when the body is stressed up to the elastic limit. So that maximum strain energy is known as proof resilience or the proof stress. So basically it is the maximum limit that the material can withstand. Next is modulus of resilience. Modulus of resilience can be defined as the proof resilience per unit volume of the material is known as the modulus of resilience, and it is an important property of the material. So you need to remember this property in order to understand the further concepts. Now what next topic that we are looking at, it's the types of loading. We know that in the previous chapter that we have solved the example based on assumption that the load applied was gradual. In most of the chapters, we have assumed that load is gradual. But in the actual practice, it is not always possible to apply the load gradually. As a matter of fact, a load may act in either of the following three cases. First one is the gradually, second one it's suddenly, and the third one it's with the impact. Now what are we going to do? We are going to discuss that the work done or the amount of strain energy absorbed in the body in all of these cases, when the material is subjected to a gradual load or a sudden load or an impact load, how much amount of strain energy is absorbed in the body, that will be explained and derived in the upcoming session. So first of all, in this particular lecture we are going to look at the derivation of the strain energy stored in the body when the load is gradually applied. This is the assumption that we have used multiple times in the previous chapters. Now it is most common and the practical way of the loading of the body, in which the loading starts from the zero and increases gradually till the body is fully loaded or it reaches its own maximum limit. When we lower a body with the help of the crane, the body first touches the platform on which it is to be placed. On further releasing the chain, the platform goes on the loading till it is fully loaded by the body. So this case of gradual applied load is very well known, or it is very helpful for us to understand how the gradually loads are applied. Now consider the metallic bar subjected to a gradual load. We are going to carry out our analysis on this particular metallic bar. So here we have list of the components or the parameters that we are going to use for our analysis. So first is P, that is the load gradually applied, A, cross sectional area, length of the bar, Young's modulus, and deformation of the bar. Now we know that the load is applied gradually. It varies from 0 to P. Therefore average load is equal to P by 2. Now what are we going to do? We are going to find out the work done. Why is it so? Because we have seen in the previous slide that the strain energy is nothing but equal to work done. So how can we calculate the work done? Work done is equals to force into perpendicular distance. So in this case particularly, what are we going to do? We are going to consider the average load and the deformation. So the average load here is P by 2, deformation here is delta L. Instead of delta L, we can write epsilon into L. Epsilon means strain into length, and ultimately we can write over here, instead of P, instead of force, we can write stress into area. So this would be our final equation of work done, or itself it is the strain energy. Now what are we going to do? We are just going to simplify this equation a little bit further. So we are going to use our equation. Instead of strain, we are going to use sigma upon E. And if we multiply and simplify it, this equation would look like this. Now, since the strain energy stored is also equal to the work done, therefore, the strain energy stored is represented by capital U is equals to this work, that is sigma square upon 2E into AL. Instead of AL, we can write volume. So instead of AL, we have written volume over here, and we know that the modulus of resilience is nothing but the strain energy per unit volume. So volume gets cancelled out, and sigma square upon 2E is our modulus of resilience. So this is how we completed our derivation. Now let's get started with the example. So calculate the strain energy stored in the body in the bar 2 meter long. So the length is already given, 50 mm wide, width is given, and 40 mm thick, its thickness or height is also given. When it is subjected to a tensile load of 60 kilonewton, so the load is also provided. Generally it is the average load. Take Young's modulus as 200 gigapascal. All the things have been listed over here, and now what are we going to do? We are going to find out our stress, that the stress is nothing but force upon area. Force upon area, force is provided as the 60 kilonewton. Instead of kilonewton, we have written 10⁻³ over here. Area is nothing but 50 by 40 that has been provided over here, that it is 50 mm wide and 40 mm thick. If you simplify this, you will get the answer of the stress as 30 Newton per mm square. Now they have asked us to find out the strain energy stored in the bar. So as this is the bar which is subjected to a tensile load of 60 kilonewton. So here they have not mentioned any kind of a loading condition. So by default we are considering it as a gradual loading. So for the gradual loading, we have derived equation of strain energy U equals to sigma square upon 2E into volume V. So put all this value into this equation. Instead of sigma square, we can write 30 over here. Instead of 2E, we can insert the value from the given data, and volume is nothing but 4 into 10⁶. How can we calculate the volume? By multiplying the length, width and thickness, you will get this volume. Simplify this and the final answer comes out to be 9 into 10⁻³ Newton into mm, or 9 kilonewton into mm. So this is how we complete our example over here. We have seen some basic definition, one derivation and its example. So in the upcoming lecture, we are going to look at the different other types of the loading that we have not seen yet and example based on them. Till then, thank you.